Hello everyone and welcome back to PyTorch programming. Today we're going to be talking about we're going to go through the demonstration of a classification pipeline, right? We're going to be doing the whole thing. We have a project, we're going to classify a seminal well-known data set built into PyTorch already, and we're going to go through the whole process of building a piece of code in PyTorch that will help us classify some images. As usual, we have a Jupyter notebook which can be run on Google Colab, already built, already ready to go, and this will be linked for you to have a look at later. So this will be discussed later. What we want to make sure that, because we're actually going to train the model this time, that we're using the GPU. That's very helpful, and as we see, we already have the GPU set here. So let's start importing a few things we need, mainly Torch and Torch Vision. This will take a few seconds to spin up the local machine. Right now we're there. I've written a bit of an explanation here that we need to, if you're using Google Colab, make sure you're using the GPU hardware. If you're using it on a local machine, obviously you can just run a piece of code like this to make sure, I'm going to remove this bit of it as well, to make sure that it is on CUDA. And we have confirmation here that the device type is CUDA. CUDA is available because I've enabled the GPU on Google Colab, and I've made the GPU to be the default hardware here. In order to, because I'm going to plot the loss live here, I'm going to use a package called live loss plot, but that's only specifically used for when you have a Jupyter notebook, you want to plot some figures on live. You don't have to use this obviously in your actual projects, but this is going to be useful for our demonstration here. So this is not something you will use for things like taking advantage of these logs and plotting loss curves. You need to be using things like weights and biases, which we looked at a few sessions ago, if you remember, or something like TensorBoard, which originally was part of TensorBoard, was built for TensorFlow, but right now it is built into PyTorch as well. It offers a lot of nice functionalities for keeping track of experiments and logging and visualization. Now I have a little helper function here that's going to turn my data loader into iterators to make my life easier, but obviously again you don't have to use this. This is just a helper function. Now getting to the actual data processing right now, we're going to use the Fashion-MNIST dataset. We spoke about MNIST a bit earlier, which is handwritten digit recognition. Fashion-MNIST is similar to MNIST in the sense that it's a small toy data set. It has the same size, same dimensions, except it's of fashion items of clothing. The class names I have listed here, things like t-shirt or top, trouser, pullover, dress, so on and so forth. Let's print out the list of the class names that we have here, and we see we have these 10 classes similar to MNIST. Now train loader and a test loader, we're going to just download the Fashion-MNIST here, similar to the example we looked at the dataset session we had some time ago. So we just run this. It's going to download the dataset for us, and it's going to extract everything, remove the compressed files itself, and then we can just print out the size of the dataset. We can see that it has 60,000 training images and 10,000 testing images, which is a decent, healthy size dataset. We can actually do some good training using this. Let's have a look at a few sample images from this. So we're just gonna use the Torch Vision make grid function to actually visualize this. We're gonna show it using matplotlib. As you can see, very low resolution, small images, and here we have actually transformed them to 32 by 32, but the original size of the images is 28 squared. Now let's get to actually building our neural network. So for this example, we have a very, very simple network. It's a two-layered, multi-layer perceptron, fully connected layers, linear layers. So when you're building your own custom network in PyTorch, we have the constructor, we have the init function here, which here we have two layers. I've defined L1 and L2. Both of them are linear layers. The first layer, L1, is receiving 1024 features, which is the size of the number of my pixels, right? My images are 32 by 32. 32 squared is 1024. And this is being connected to 512 neurons, so there's a lot of dense connections here. 1024 is getting connected to 512. And then the second layer is going from that 512 to 10, which is the number of my classes. Fashion-MNIST has 10 classes. Now I need to define this forward function, which defines how the data is going through the network using the layers I have defined earlier. So my X being the input is going through the first layer. Then I have a activation function, ReLU, which is, you will learn about that later. There are obviously a variety of activation functions. You can even build your own custom one depending on the type of application you're working with. Here we're using ReLU, and then it goes to the second layer, and then after that it's unconstrained. It can be anything at the end, and we return X. That's a very simple two-layered neural network. Now, obviously, in the real world, again, we're not going to be using something like this, but just as a demonstration for right now, this will do. Now, then we're going to initialize our model. We're going to put it on device, and if you remember, we set device to be CUDA earlier. If I can write device is towards that device CUDA. So it is on the GPU. Now, let's run this. I have made it so at the end we're just printing out the model. It's just going to give me the basic structure of the model, which, as you see, is two layers. And now the neural network should, because we put it on the GPU, it's already on the GPU, and it should have the requires grad flag set already. Now we can even look at the specific weight. So here I've printed out model.L1, which is my first layer, .weight, which is going to give me the actual weights of the model. At this point, it's just random initialization. But you see that they are already on CUDA. They are already using the GPU, and the requires grad is true. This will enable backpropagation, as we talked about in the last video. Now, we can obviously start implementing the backpropagation process ourselves, try to optimize the layers in our network, the parameters, calculate the gradient, do something like stochastic gradient ourselves. But obviously we're not going to do that. PyTorch offers us a lot of optimizers already built in. In a lot of projects you will see that Adam is commonly used in many of the state-of-the-art papers out there. Adam is very effective. It takes advantage of the concept of momentum. Based on the moving average of the gradient, it decides how much optimization should happen at any given point for each parameter separately, and it does that very effectively and efficiently. So here we're going to just create our optimizer, Adam, which passes our model parameters in there. That's the parameters that we are optimizing, the parameters of our model inside our model. The learning rate initially is 0.001. So let's run this. Our optimizer is now set. We're just using a bunch of its default parameters. Obviously, hyperparameter tuning is something you will have to deal with later. We'll have to decide exactly what the parameters have to be to get the best performance out of the model that we are building. But that's a story for another time. Some early preparation for the actual training process. We're going to go through a number of steps, right? So there are two general concepts it would be good to know. One is epoch. Epoch is when we train the entirety of our data set, train on the entirety of our data set once. That's one epoch. Now, obviously, sometimes we train multiple epochs, thousands maybe, meaning we go through the entirety of our data set thousands of times. And a step or an iteration is when the optimizer takes a step, meaning optimizes the neural network after receiving one batch, one forward pass and backward pass over one batch. That's one iteration or one step. Here I'm just going to train our model for a specific number of steps. So starting from 0, then I'm defining the loss function. The loss function here is cross entropy. You will learn about this later. It's basically for categorical distributions, right? So I have a number of categories I'm trying to optimize. I mean, you can have something like mean squared error, but it's obviously better to take advantage of the specifics of the project, like in this case being categorical. It's best to take advantage of that and get the best performance. Now here, this live loss I'm creating in order to plot the losses lives, and logs is for the same purpose as well. So let's initialize these. The loss function here being an important part of the main loop, which we will see. Now let's get to the actual training loop. This is the main part of our training process, which is very simple. PyTorch makes things very simple, very nice, and at the same time it gives you a lot of flexibility. You can change a lot of things. You have full control over everything still. So the way I've coded this is I'm just going to train this for 5,000 steps. So I have discarded the idea of epochs. I'm not going through the entire, it might be 3.5 epochs depending on the number of batches I've created. Let's look at that. Actually, I've given very large batch sizes, I believe. So for my training data, I have batch sizes of 256. And for my test, it's 512. I mean, obviously I can fit more of the test data into my GPU memory because test data don't need gradients, right? I'm not backpropagating over my test data, but for training data, I need to have that computational graph. That gradient function is going to take up a lot of memory itself. So here we're going to train it for 5,000 steps. Then I'm going to go over the train loader, the data loader that I created earlier. I'm going to extract a batch out of this. The batch is going to have an input tensor X and a ground truth, which is the label. I'm going to put these specifically on the GPU, right? Remember that all tensors by default are on the CPU. You have to put them on the GPU yourself if you're going to use GPU hardware. Then I'm going to change the shape of the input tensor. So the images that we're receiving right now are going to be 32 by 32, right? They're two-dimensional matrices. It's an image. But I am using fully connected linear layers. So I expect a single dimensional vector of 1024. This line is going to do that for me. So I'm going to view my input tensor as just the elements placed in a one-dimensional rank 1 tensor. Then I'm going to pass the data, the input, through my model, and I'm going to get the output. Output is now my prediction. This is the output of my model. Now, then I'll calculate the loss function. The loss function was defined earlier as my criterion, which is it's a cross entropy loss. And this is the cross entropy between my output, the raw output of my network, and my ground truth. This is going to measure the distance itself, this categorical distribution, and try to minimize that later on. Now, in PyTorch, remember, in every iteration of our loop, we need to make sure that the parameters are actually explicitly, the gradients are set to 0, right? We want to, for every backward step, we need to make sure that the gradients are set to 0. Nothing is left over from another operation. And then we call this the magical line, if you remember from the last session, loss.backward. This is going to go backwards, walk back through the computational graph, and it knows exactly what operations have happened. Calculate the gradient of the loss function with respect to every parameter of my model. And then I call optimizer.step. This is going to adjust my parameters slightly based on the gradients calculated in the backward pass. I have optimized my neural network weights by just calling these few lines. Very simple, very easy, yet very effective and powerful. Then I'm going to add one to my step for my main outer loop. Then here to calculate the accuracy, I'm just going to calculate the argmax. See what is the maximum value in that vector, and if it is equal to that, then I'm going to calculate the mean of that and times 100 to get the actual percent value. Every 50 steps, meaning every 50 times I update my neural network, I'm going to run the test on the test set. I have 10,000 images for my test set, and I'm going to log the performance of my neural network every 50 steps as well. During the testing process, I don't need gradients. I'm not updating my neural network anymore. So I have this with torch.nograd. This function is removing any gradients from any of the tensors that might be there, even my model itself. Then I'm going to get the test loader, get the batch out of the test loader, put this batch into, again, X and GT. I have to do the same thing, reshape my view of my tensor to a single one-dimensional rank 1 tensor, basically. Get the output, calculate the loss. This is just for logging purposes. Obviously, I don't actually need the loss for my test. I'm just trying to measure the performance of my model here. Calculate the argmax, measure the accuracy, and then using that live loss plot thing that we have, I'm going to here essentially create this data structure logs like a dictionary. I'm keeping the loss, test loss, accuracy, and test accuracy, and then I'm going to plot them out so we can actually see what is happening to our losses and accuracies for both test and training data. So as you see, the loop is actually quite simple. It's not very difficult, yet because it's all separated, I still have full control over every aspect of my model. I can change things very easily. So let's run this and sit back and see what happens to our model, what plots we're going to get. So as we see, we have started creating the plots, and the accuracy is going up for both training and validation. The loss is coming down for both training and validation for my test set. Obviously, there is going to be a discrepancy between the test set and the training set, but that can be, I mean, if it's too much of it, it can be overfitting. We want to minimize that, yet at the same time, some level of that is expected. It's a bit noisy. I mean, obviously, if you calculate the running mean of the loss or accuracy, it gives you a smoother curve there. But that I haven't done that. This is just for demonstration purposes. I'm just calculating I'm just keeping the actual loss of the last step at every 50 steps. So, but we see that we get a clear, consistent downward trend for our loss. So the loss is actually going down, meaning the distance between the output of the model and the ground truth is actually being minimized. And the accuracy, there is an upward trend, a bit more noise with our training set, but we can see even for our validation set that things are going up. And we get the actual values here as well, if we want to keep track of those also. So the point being taken away is that it's actually very simple yet very powerful, and obviously you'll have to go through the documentation of PyTorch yourself to get a more detailed overview of what's possible there, but this should actually give you a general idea of what PyTorch is capable of. I hope you have learned something. Thank you very much.